Okay, thank you so much for this wonderful introduction. I've been sitting here listening many exciting talks, including the one just by Rohit. I think uh, I want to add something from our research team's perspective. Hopefully, this will give some other insights or raise some discussions among the audience. So I think I should be able to skip what is DPU because so many things has been discussed. Basically, SmartNIC with some specialized or general purpose cores, memory components on the device. So for NVIDIA DPUs, right? So there is a lot of interest these days, especially we've been hearing so many talks from NVIDIA Vox and as well as others. My team also have been working on the NVIDIA DPUs for multiple years now. Thanks to NVIDIA's donations, we are able to study from BlueField 1 to BlueField 2 and BlueField 3 different architectures. So these two pictures basically show the abstracted architecture of the BlueField 2 and the BlueField 3. So as the audience asked, actually, DPUs are not only from NVIDIA, right? There's some other vendors also providing their own designs for DPUs. For instance, like in addition to NVIDIA's BlueField, we have like Marvell's Liquid I/O, as well as the Xilinx SmartNIC solution as well. So they choose different. Each of them choose different way to implement their own DPU solutions. So based on our study, what we found is DPU, just as many people said already, is good low power devices, right? Remember there was discussed like power and consumption kind of things. And the computing units and hardware accelerators are also widely available. Just like Rohit said, there's a good amount of resources available. So that's why we want to offload or we want to utilize DPUs for the applications. In the meantime, of course, it can help us improve server resource utilization because now if you offload something to the DPUs, then you can better utilize other resources for more useful work. So another good thing is mostly because of many of these DPUs provide SoC cores and the general purpose computing units as well as operating systems. So relatively speaking, it's easier to program. And it provides many flexibilities for different modes and relatively speaking, compared with other solutions, performance-wise is also good. So what is not good, or at least needs some kind of enhancements in the future, in our opinion, is first of all, it brings more architecture level complexities, which limits the adoption for a more wide range of applications. That's why Rohit mentioned, right? If we want to design the UROM, which can help to offload more applications on DPUs. That's good direction in my opinion. And also the second thing is efficient use of accelerators requires significant effort. For instance, if you look at the DPU architecture, there are many accelerators available, but how to use it or how to efficiently use it is especially still need many expert knowledge as well as many designs. I'll show example later, okay? And sometimes we also need a careful hardware software co-design to really achieve the benefit in the end. So with this, let me discuss two example work from my group. The first one focuses on the architectural insights. We want to share that what happens internally of the DPUs and where are the bottlenecks. And then we show that next how to improve some workloads like data compression. So as I mentioned earlier, if you look at the BlueField DPU architectures from BlueField 1, 2, 3, we can see that, of course, network speed and the capabilities keep improving, right? 6, 5, 6, 6, 7. And there's many modes available. Like broadly speaking, we can split it into on-pass mode and off-pass mode, okay? And between the constant DPU communication, you can either use RDMA primitives or you can use DMA primitives provided by DMA engine in the BlueField 2 and BlueField 3. So compute memory, I think, has been discussed by other talks, and I want to skip that for this talk. So first of all, I want to introduce one thing before we go further about the communication level studies. One is about what is DPU modes, okay? So DPU modes control how packets are handled within the DPU before reaching the host. So broadly speaking, like I said, there's two modes available. One is called off-pass. Basically means the network traffic to or from the host bypass ARM cores. Okay, DPU functions as an independent server. Host supports both either Ethernet mode or InfiniBand card. And for the on-pass mode, Ethernet transport is supported for the on-pass mode only currently for BlueField DPUs. And it's more complex, so that's why I cannot discuss this one in this single slide. I have to use multiple slides to discuss on-pass mode separately. So first of all, on-pass mode allows offloading host packet processing operations, so such as packet forwarding or filtering. And it has two different passes. One is called slow pass. Basically, DPU ARM cores can sit on the critical network path between host and NIC ports. And the other one is traffic load pass, which packet processing rules can be offloaded to the embedded switch or E-switch. And then under these two paths, we have 5 different submodes available, in fact. So for first one, for the slow pass, on pass, which if you zoom into it, we have like Open vSwitch kernel or submode 1, which actually run the OVS kernel on top of ARM cores. Or we can use OVS with DPDK, which move this one to user space, and then we call this is called submode 2. Or we can purely DPDK plus pool mode driver, which is called submode 3. So if you look at this path, the message go through the slow pass and then reach to the OVS or DPDK and then reach to the host. That's called slow pass. And the other one is called traffic offloading pass. So basically, you can use some hardware offloading engine which to speed up the OVS kernel as well as OVS DPDK mode, which called submode 4 and 5 respectively. So this is the path corresponding. So overall, if you summarize it, you can see that even for the on-pass mode, we have 5 different sub-modes which are available. So you can see that this definitely needs some studies to differentiate the performance as well as the characteristics correspondingly. So this motivated us to design. This is just one aspect of the DPU's complexity, okay, for the mode perspective. But from other perspective, we can also come up with different things to examine the performance as well as the other limitations. So that's why we came up with a benchmark first called DPU EDO bench. Basically, we want to discuss from network perspective, DPU modes perspective, DMN engine perspective, memory utilization, and also as application case studies, how to leverage these different resources from the application perspective. We use a key value store as example. So we have this benchmark. We called we open sourced it already, so that you can download it and you can reproduce everything I'm going to talk in the next few slides. So if you have, because of time, I cannot zoom into a lot of details. So if you have interest, please go to please take a look at the paper just published in ICS. We presented in this week. A lot of details over there. So these are test bed. We systematically run our benchmarks on top of BlueField 1, 2, 3 generations. We try to observe what's going on over the years, and which is improved, which is not improved, or so on and so forth. So from the network perspective, because of time, I cannot discuss RDMA paths. Please feel free to read our paper because I think RDMA being discussed by many people already. So that's why I'm trying to focus on the TCP paths. So for the TCP path here, basically we need to remove multiple things from these trees, right? So this is the only thing available. If you just want to evaluate with TCP path, slow path, as well as the traffic offloading. So we are focusing on these 5 submodes in the next few slides. So, but of course, we observed many other idiosyncrasies or advice for the DPU vendors. Because of time, like I said, I can only focus on N1, which is the if you traverse the ARM cores in the on-pass submodes, what happens? Okay, overall, we see that there is 1.3x to 2x overhead if you do that. For some other observations, like how about the rocky performance as well as DMA, DPU, and remote host RDMA latency, so on and so forth, we have some other observations in our paper. So for now, for TCP pass, you can see that our experiments is conducted in this way, or the benchmark is in this way. So DPU actually running purely on the client machine configured in off-pass mode. And for server, we configure them into different submodes one by one. So in this case, you can see that if there's any overhead, it actually is from the on-pass mode. So if you look at our results, you can see that first of these slides, we're trying to discuss for submode 1 and 2. You can see that for submode 1 and 2, you can see, especially for submode 1, there's a 3.9x latency, bandwidth increases from BlueField 2 to BlueField 3. So which means definitely BlueField 3 brings some extra benefit from bandwidth utilization. And for submode 2, you can see that there's a 2.2x increase from BlueField 1 to BlueField 2 and a 1.4x from BlueField 2 to BlueField 3, which means this in this submode, the bandwidth keep improving over the years or over the generations. That's good. And then this one is trying to discuss submode 3. Submode 3 can achieve higher host bandwidth compared to submode 2, for instance, 3.9, 2.7, 1.x higher bandwidth for different generations of BlueField, respectively. And higher packet forwarding capability of submode 3 due to the lack of obvious overheads compared to submode 1 and 2. And we also see that if you compare this submode 4 and 5, we can see that submode 4 and 5 show performance which comparable with off-pass mode, which means submode 4 and 5 with the hardware offloading, we can achieve much better performance. If you look at the IPC number, that's actually show why the bandwidth get improved as well. So overall, you can see, as I mentioned earlier, if the packet travels over the ARM cores in the on-pass submodes, it will incur a significant amount of overhead on the host across different BlueField DPU generations. So unfortunately, we don't have time to discuss other idiosyncrasies, but please feel free to take a look at the paper. And we're also trying to discuss a little bit about the DMA engine, because this DMA engine was brought from Things BlueField 2, and it can be separately used in addition to the RDMA engine internally, okay? But unfortunately, there's no benchmark available, so we designed a DPU DMA benchmark by ourselves. We are trying to show that what's going on over here and what kind of performance characteristics we can observe. So we observed a lot of interesting things here. We have summarized into 5 different advices. So because of time, we can only discuss the first one probably, but feel free to take a look at others. So for the first one, actually it's pretty easy because like Rohit mentioned, right? You can do H to D, D to H, or D to D, D to H, so on and so forth, many combinations now. So including, you can also do like event pooling or event-based notification or pooling-based completion kind of things. We want to see that from BlueField 2 to BlueField 3, what happens over on the latency as well as the throughput. So here you can see that the latency of event-based DMA operations initiated by the host shows an average of 3x or 1.7x lower latency than DPU initiated across BlueField 2 and BlueField 3. And if you look at the throughput, the pooling-based DMAs do not depend on the initiator, actually. So we observe 5.8x or 3.5x higher throughput than event-based DMAs, no matter you do it from host side or DPU side. So which means the event-based DMA performance depends on which device is the initiator, which actually bring some other complexities in your code, actually, if you try to use this DMA engine. Like I said, unfortunately, we cannot discuss others, but please read our paper. And then we use an application, like we use two cases. One is Mica is TCP-based key value store. We also use the herd, which is the RDMA-based key value stores. We try to evaluate what's going on, and from application perspective, what kind of performance we can observe. So again, we can only discuss one here. Here, basically, we see that KVS server should use sub mode 4 and 5 if you choose on-pass mode for better performance. Here, we show some performance comparisons. We can look if you configure your applications or use the right mode and the right primitives, we see 6x to 10x performance differences. That's big differences, in fact. So like what I mentioned earlier, if you want to use the on-pass mode, 4 and 5 might be something you should choose compared to 1, 2, 3. So we try to summarize. We do all the things. Try to generate this table. Basically, what's the recommendations for the vendors if you design your next generation of the DPUs? So we actually summarize something over here. For instance, we probably need the enhancement of the DM engine from some perspectives, and the network on-pass cores or computing units still significant amount of improvements in our opinion, and the memory. We think that there's some cache utilization problems in BlueField 3, so on and so forth. Okay. So overall, we summarize the 14 valuable advices for DPU to show the DPU evolution over the years from the network, DM engine, memory, as well as application perspective. So hopefully these things can help for the future DPU hardware designs. And we open source our benchmark so that everybody, if you want to learn how to use these things, our benchmark provide a very simple application or very simple examples to help you to understand the DPU architecture deeply. So then let me quickly jump into one workload acceleration from what we discussed earlier. So here we try to use compression as an example. Okay, compression, many people definitely know that you broadly divide into lossless compression or lossy compression. So we come up some, we collect some benchmarks on datasets from the community. We're trying to test with 7 datasets, 2 different hardware platforms, BF2 and BF3, and 3 lossless compressor and 1 lossy compressor from 6 different dimensions. So let's observe what happens internally. First one, if we use the different way to compress the data from like deflate, zlib, or AC3, those kind of things. And then we use ARM cores, also compression engine. Compression engine is the hardware accelerator available in the BlueField 2, okay? So here the details I will skip it. The suggestion I'm gonna give to you is if you use the compression engine, which is C engine we showed over here, you can significantly improve your performance and you reduce the SoC utilization. And if you look at the breakdown time about compression time as well as the decompression time, what we want to bring to you is we probably, if you use the compression engine, the compression time can be significantly reduced. However, the decompression time actually has some inefficiencies over there. Okay, we don't see any significant benefit even you use compression engine for the decompression. So we then further break down what happens internally. So we see there are many overhead involved with Docker environment initialization, as well as the buffer preparation, so on and so forth. So we are trying to think that if we want to use this kind of compression engine for your data compression pipelines, then we need to mitigate this kind of associated significantly for both compression and also decompression. So we compared BlueField 2 and BlueField 3. We're going to see that whether the things happens for both of them. We do see that BlueField 3 kind of improving a little bit from the speed perspective. However, BlueField 3 kind of, lose some functionalities in their chips, which is something we want to highlight. So to summarize, the trade-off of using DPU for compression is some compression hardware accelerator can improve, but this is not trivial, even you want to get the benefit of application. So we have a paper in RPDP 24, which actually summarizes all these things in details. So I think one of the audience mentioned something like, okay, now we have DPUs, we have so many interfaces, APIs, and so many libraries available. It's not easy to use for applications, right? So this is the motivation why we came up with a new library called Pedal. So we are basically trying to provide uniform lossy and lossy compression APIs and architectures for the applications. So basically, application only need to understand 4 APIs. You need compress and decompress and finalize. And then internally, so this is the comparison. If you use Pedal, you need 8 lines of code. You can implement the highly optimized compressions in your code. But if you use Docker, you need 500 lines of code to design what I discussed in the previous slides, and also it's hard to optimize as well. Not only that, if you look at Docker, it only supports limited compression operations or compressors. With us, we can support many 7 different type of combinations actually, and including lossy and lossless compressors. Just use same API. We can support both lossy and lossless compressor on BlueField DPUs with all the optimization we discussed in our paper. So if you look at the performance, you can see that with our optimizations, sometimes we could improve like hundreds of times speed up or 70 times performance speed up for both deflate as well as ZD. And for SD3, this is a lossy compression. We collaborate with our Organization Labs. We are able to port their library and also redesign their library to use DPUs, pipelines, and parallelisms. We can achieve like 1.5x improvements. And then we also integrated our designs into the MPI. We see that from point-to-point communication, we can uniformly improve the performance if you use our library. Okay, across different message sites as well as the data sets. And then for collectives, similarly, we can improve the communication performance if you run this on top of DPUs. So let me quickly make a conclusion here. DPUs give a lot of opportunities, but in the meantime, a lot of challenges as well. We share our findings and acceleration from the DPU idea bench, also Pedal. We hope that we hope DPU may be more promising for future parallel and distributed system applications. But again, there are many open questions needs to be addressed. So that's why I want to announce that in my team, we initiate a new project called Open Dota. This is just funded by NSF. So we hope that we can open source everything we did in our research group and also collaborate with the community so that it can cover different DPUs. Acknowledgement, my group members, as well as the vendors, as well as the NSF, DOE for their funding to support us. Thank you so much. Sorry, running a little bit more time, so I'm happy to take any questions.
So thanks to speaker. Interesting talk with some feedback to the vendors. Do we have questions?
Can I ask one question?
Yeah, sure.
Yes. Yes,
Welcome,
sure.
Mr. President.
So yeah, so we have been we had the DPUs for a long time, but we couldn't find real applications to run on them and leverage their capabilities. So it brings me the question of the value of DPUs with respect to the cost which one incurs to get them on their systems. Do you have any advice on that?
Yes, that's very good question. I mean, this based on what I just mentioned, right? There's so many reasons why you cannot easily get a performance benefit to the applications because of the complexity we discovered from the paper. So that's also our motivation why we put together these projects. We are trying to share our studies and share our code base. One example we shared in this project is we are going to present our HPDC work soon. We are trying to see that whether DPU can optimize the key value cache or key value stores. That's actually one of the good applications which utilized by many HPC, AI, as well as data center workloads. That's one application we're targeting currently. But of course, like I said earlier, MPI with compression and with other optimizations mentioned by Rich as well as Rohit, that's maybe something we can do as well. But of course, how to transparently give the benefits to all kinds of MPI jobs still are challenges, in my opinion. Thank you.
Thanks, Xiaoyi.
We have another question from the audience here.
Thank you for the talk. Nice work. So you said that you're trying to find the application benefits, and it was proven in the past, for example, that different storage acceleration in the DPU can actually give benefit, especially for HPC applications and AI applications. Are you planning to extend your work also to cover benchmarking on the storage size, for example, block, file system, etc.? Or you're mainly focusing on the networking part and the compression and offloading of the data path, and not the surrounding that requires also that maybe can take good effect?
Yeah, that's a very good question. So far we didn't evaluate with IO workloads yet. That's something definitely we need to do in our next steps. So far we only mostly focus on the compute, memory, network, in-memory kind of applications. But IO definitely something can be done as well. Yes, thank you. We didn't do that yet.
One final quick question, if there's any. Well, if not, then we thank the speaker again. We thank all of the speakers in this session.
Thank you.